Around 1000 BC, the ancient Phoenicians, known for their seafaring and shipbuilding expertise, developed practical methods for maintaining their vessels. They utilized tidal flats to repair and maintain their ships. By beaching their vessels during low tide, they could scrape off marine growth, repair hull damage, and ensure their ships remained seaworthy. This practice highlights their ingenuity and understanding of maritime logistics, contributing to their success as one of the most prominent trading civilizations of the ancient world. By 100 CE, the Romans, renowned for their engineering and maritime prowess, constructed tidal grids in Ostia, the primary port city serving ancient Rome. These grids consisted of structured platforms or areas along the harbor where ships could be guided during high tide. When the tide receded, the vessels would rest on the grid, allowing easy access for inspections, cleaning, and repairs. This innovation significantly enhanced ship maintenance efficiency, enabling quicker turnarounds for trade and military vessels. It also reflects the Romans' advanced understanding of tidal patterns and their ability to adapt engineering solutions to maritime challenges. Ostia's tidal grids were crucial in maintaining the Roman Empire's robust naval and commercial networks. By 1000 CE, during the Song dynasty, the Chinese demonstrated remarkable advancements in maritime technology by creating wooden caissons for ship maintenance in harbors. These caissons were essentially watertight enclosures that could be floated into position around a ship. Once in place, they were sealed and water was pumped out, creating a dry environment around the hull for inspections, cleaning, and repairs. This innovation was a significant leap in ship maintenance technology, allowing for more efficient and controlled work on vessels without the need to move them to tidal flats or dry docks. It also reflects the Song dynasty's emphasis on maritime commerce and naval strength, as the period saw the expansion of Chinese trade routes and technological innovations such as the magnetic compass. Wooden caissons were an early precursor to the modern dry dock, showcasing the ingenuity of Chinese engineers during this era. In 1495, King Henry VII of England oversaw the construction of the first dry dock in Portsmouth, a significant milestone in maritime engineering. This dry dock, located in the harbor of what would become a critical naval base, was designed to allow ships to be brought in, sealed off from the sea, and then drained to water, creating a controlled environment for maintenance and repairs. This innovation revolutionized shipbuilding and maintenance, enabling more thorough and efficient work compared to traditional methods like tidal flats or caissons. The dry dock was part of Henry VII's efforts to strengthen the English Navy, which included the construction of advanced warships like the Mary Rose. Portsmouth's dry dock laid the foundation for England's naval dominance in the centuries that followed, marking it as a significant moment in maritime history. In 1515, the Arsenal of Venice, one of the most advanced shipbuilding facilities of its time, introduced floating dry docks with an ingenious design utilizing pontoons and chain systems. These floating dry docks allowed ships to be raised out of the water for maintenance and repairs without requiring fixed infrastructure like traditional dry docks. The system worked by maneuvering pontoons, large, buoyant platforms, beneath the ship. Using chains and pulleys, the pontoons could be adjusted to lift the vessel above the waterline. This innovation reflected Venice's maritime expertise and its critical need to maintain a powerful fleet for trade and naval defense. Floating dry docks provided flexibility, enabling ship repairs to be conducted in various locations, not just in permanent harbor facilities. This advancement reinforced Venice's position as a leading naval power during the Renaissance and demonstrated its ability to blend engineering ingenuity with the demands of maritime commerce and warfare. In 1833, the United States Navy, U.S. Navy, constructed its first permanent dry dock at the Boston Naval Yard, now the Charlestown Navy Yard, in Massachusetts. This dry dock, known as Dry Dock 1, was a significant achievement in American naval engineering, designed to support the growing needs of a modern naval fleet. The project began in 1827 and was completed in 1833 under the direction of renowned civil engineer Loamy Baldwin Jr. It featured granite masonry and advanced mechanisms for the time, enabling water to be pumped out to create a dry workspace for ship repairs and maintenance. The first ship to use the dock was the USS Constitution, which underwent restoration there shortly after its opening. This dry dock marked a turning point in the U.S. Navy's capability to maintain its ships domestically, reflecting the nation's growing maritime ambitions. It established the Boston Naval Yard as a critical hub for naval operations and contributed to the United States' ability to sustain a strong and reliable naval presence. Pearl Harbor's Dry Dock 4, located at the Pearl Harbor Naval Shipyard in Hawaii, is one of the largest dry docks in the United States. It is capable of accommodating vessels as massive as modern U.S. Navy aircraft carriers, including the Nimitz-class and Gerald R. Ford-class carriers, which are among the largest warships in the world. Dry Dock 4, completed in 1943 during World War II, was part of a massive expansion of Pearl Harbor's repair and maintenance facilities. Its construction played a critical role in supporting the Pacific Fleet, especially after the devastating attack on Pearl Harbor in 1941, which underscored the need for robust ship repair capabilities in the region. Today, Dry Dock 4 remains a vital asset for the U.S. Navy, allowing for maintenance, upgrades, and overhauls of the fleet's largest and most technologically advanced vessels. Its size and infrastructure underscore the strategic importance of Pearl Harbor as a hub for naval operations in the Pacific. Dry docks and floating dry docks are essential maritime facilities that enable ship maintenance and repairs by providing access to systems and structures typically submerged below the waterline. This capability is crucial for ensuring the safety, efficiency, and longevity of vessels. Dry docks are indeed ideal, though not strictly necessary, for the replacement of anchors and anchor chains. The controlled environment of a dry dock provides several advantages for this process, but alternative methods are often employed when a dry dock isn't available. Attaching a new or reconditioned anchor to an aircraft carrier and hoisting it using the ship's windlass is a carefully planned and precise operation due to the immense size and weight of the anchor and its chain. The hole through which the anchor chain passes is called the hawse hole, a term derived from the Norse word hals, meaning throat. This name reflects the function of the hawse hole, as it acts as a passageway for the anchor chain, much like the throat is a passage for food and air in the human body. Dry Dock 4 at Pearl Harbor, one of the most significant dry docks in the United States, has impressive dimensions and a robust design to accommodate some of the largest vessels in the Navy, including modern aircraft carriers. Safety considerations during the flooding of Dry Dock 4 at Pearl Harbor are crucial to ensure the process is smooth and does not damage the vessel or the dry dock infrastructure. Several factors are carefully monitored throughout the procedure to maintain the integrity of the ship, the dry dock, and the surrounding environment. The flooding process for Dry Dock 4 at Pearl Harbor, which involves filling the dock's 50 million gallon capacity, typically takes about 40 to 45 minutes. This rapid yet controlled process is made possible through the use of gravity-fed systems and multiple culverts that manage the water flow efficiently. Once the dry dock at Pearl Harbor, or any similar dry dock facility, is filled with enough water to float the ship, such as an aircraft carrier, the process of steering the vessel out of the dry dock begins. This is a delicate operation that involves coordination between the vessel's crew, tugboats, and dry dock personnel. Underway replenishment, UNREP, is a critical operation for naval forces, allowing ships to receive supplies, fuel, and other essential materials while at sea, without needing to return to port. Sailors receive extensive training to perform UNREP safely and efficiently, and this training often includes simulated exercises with two moored ships at a naval base to replicate real-world scenarios. When two vessels are connected during an underway replenishment UNREP operation, the procedure is called connected replenishment CONREP. This method is commonly used for transferring fuel, ammunition, provisions, and other supplies between ships while both vessels are underway, i.e., moving at sea. It involves the use of various equipment, such as fuel hoses and transfer lines, to physically link the two ships and allow the safe transfer of goods.